Hi, I'm Sok Min Hwang. I'm very honored to present about a paper, PubSub Sum, a content summarization PubSub protocol on information-centric networks. In 2017, the U.S. Army selected 6 motorization priority and decided to invest $1.1 billion for these 6 projects to build more critical force. It means that 6 are the leading technology for U.S. Army, and it is not surprising that tactical network is one of the top 6 priority considering the importance of network system in the modern warfare. With the increasing importance of the network system, network infrastructure itself becomes a main target of adversary to deny information sharing among friendly forces. Also, those attacks are getting more advanced and sophisticated than before. In this sense, military communication experts are looking for reliable and robust communication solution in the contested space. However, the solution must be adaptable and compatible with the legacy system because to upgrade legacy system is considered to be very expensive in terms of the time and cost, especially for the scale of military. Therefore, we focus on minimizing data volume. There are mainly 2 types of approach to minimize the data volume: summarization and compression. Compression can be general service while it is subject to time-space trade-off, but this technique requires usually long time to compress and decompress data unless there is expensive hardware to support the operation. Summarization, however, is to select a subset of the data from a whole dataset. This is fast and efficient, but hard to generalize because sampling needs are application specific. For example, in the disaster response application, spatial image samples would be better to quickly understand the current damage by disaster, but temporal image would be better for understanding the progress of disaster. Therefore, our work uses application-specific algorithm to produce the representative samples that best suits the application purpose. Our relevant work, Infomax, proposed such a service in the transport layer to minimize semantic redundancy of transmitted contents and maximize information coverage. It periodically organized the data and pushed the representative samples first. For example, if disaster happens near Prague, it organized the data according to the categories such as fire, flood, sinkhole like this. Then it pushes the representative data to minimize the redundancy and maximize information coverage. However, Infomax has 2 limitations. First, Infomax is designed to share the static data set that does not change after transmission. It is problem for streaming data such as video. Second, it's designed to communicate between one producer and multiple consumers. So in this paper, PubSub resolved the limitations by designing 3 aspects: supporting to summarize stream contents, many-to-many communications, and a new type of congestion control. Like this. So we'll look at them in detail in a minute, and also I will show you the implementation and evaluation details to conclude our work. Let's start by handling streaming content. Infomax prioritizes all the data and generates a single list of available named objects that can be broken down hierarchically by topic and subtopic. Let's call it the name catalog. Consumers request a piece of data named catalog on a given topic or subtopic called a page that contains a fixed number of names. Once a consumer receives all the content of a retrieved page, the next page can be requested if more detail is needed. In this manner, consumer can control the amount of content retrieved until their summarization needs are met. But the problem is that name catalog is difficult to update once published. This complicates support for real-time streaming application. So to remedy this problem, we focus on individual stream as the unit comprising the summary. The namespace breaks down the set of available streams in a hierarchical manner such that more redundant streams share a longer name prefix. In addition, each publisher periodically creates a sublist called volume. An example can be found in this figure, and a name catalog consists of several volumes containing content streams. As before, each volume has a page of the content's name, where each page has fixed number of names. The update period decides the number of the volume and page. Thus, the shorter the period, the quicker the update, but the higher the communication overhead. Next, let's talk about how to support multiple sources. Our algorithm supports multiple sources by allowing them to exchange the name prefix of the data that they carry. If NDN-like routing protocol is running, it may exchange locally registered prefix information. Once the prefix information is shared, a subscriber can construct a prefix or topic tree as this figure. For example, the figure shows four publishers whose names are /street_A/block1, /street_A/block2, and /street_B/block3, and block4. And each of these publishers is a street camera that monitors traffic congestion status and periodically generates available content names so that the subscribers are aware of the existence of newly created content. If the network resources are sufficient, the subscriber needs to select a subset of the publisher to constitute its data summary. An effective way would be to minimize the redundancy of content. So in this example, two cameras on the same street are more redundant than other pairings. Therefore, one camera of each street can be removed from summary or unsubscribe to save some bandwidth. Lastly, let's talk about how to manage congestion. Traditionally, congestion control mechanisms adaptively control the sending rate of individual sources according to the network condition. But there have been several efforts studying congestion control mechanism in ICM. Current approaches are categorized into three groups: receiver-based, hop-by-hop, and hop-by-hop interest shaping, and hybrid approach. However, PubSub complements prior solutions using the application layer technique. In this work, we combine our application level congestion control mechanism with one of the receiver-driven approach. This algorithm works similar to the current TCP congestion control. It maintains a congestion window that defines the maximum number of interest packets in transit. Initially, it doubles the window size until congestion is detected, which is slow start phase. But when the congestion is first detected, it halves the window size and switches to AIMD phase. If congestion is not detected, the window size increases gradually. Otherwise, the window size decreases quickly. Whenever a consumer issues a new interest packet, it triggers a time to measure the package round trip time, RTT, between the interest issue and the data arrival. If the RTT delay is longer than expected time delay, it considers that congestion occurs in the network. If the network gets congested, the consumer signal to the subscriber so that it can adjust its data volume to retrieve. Otherwise, the subscriber assumes that the network is sufficient to manage the current volume of data requests. Based on this algorithm, we developed an enhanced congestion handling solution. A subscriber interested in data under some tree prefix first starts by retrieving for a certain period. The subscriber increments the number of branches from which data is requested by picking a branch that is least redundant with the current subscription. We say that a new branch subscription is added. The retrieved summary is collected from all the subscribed branch of the tree defined by the original prefix. The algorithm for incrementing branch subscription is merely a tree traversal that always selects the least visited branch first with a leftmost tiebreaker rule. In this figure, if /street A /block 1 is subscribed, then the algorithm picks /street B block 3 next. On the other hand, if network congestion is detected, it decrements subscription. Now that we have talked about three aspects of system design, and let's move on to implementation details. We provide a library package called Athena that can be effectively scheduled data retrievers according to the specified application needs. The PubSubSum protocol is an Athena layer component placed between the application and the transport layers. It offers APIs to publish and subscribe contents under a specific prefix or topic. But when an application asks to subscribe to the prefix, the subscriber collects the matching prefix from the network. Then it prioritizes the collected prefix in the least redundant order based on names and starts subscribing to the very first one in the list. It first asks the meta information about the served content set, including the volume number and its page number as described in this figure. Depending on the application type, it can select either the first volume or the last one. If an application does not care first page of the volume to get a prioritized contents list, if application does not care about historical data, it will choose the latter. Once the volume number is decided, it retrieves the first page of the volume to get prioritized contents list. Finally, the subscriber can request actual contents based on names in the given page. This process is iterative until the application cancels the subscription. Okay, now let's move on to evaluation details. We evaluate the system in two different environments. The first environment is Mininet, a widely used network simulator that flexibly can configure the network environments including link speed and network size. The second one is Real Device Testbed using Raspberry Pis. The purpose of the testbed is to show that the protocol can run on actual devices and that result match simulation. For Mininet experiment, we have composed a hypothetical scenario for better understanding of the use of PubSubSum protocol. The scenario is about company Renaissance, where a company is searching a particular area and the company commander wants to have periodic reports from subunits. For convenient naming, let's say the every fourth unit is a headquarter, and every squad has a mobile camera and stream image every second for 30 seconds to the company commander. To simulate this, we create the grid topology with 16 nodes as shown in this figure. A name for each node is hierarchically composed, such as /company /platoon1 and /squad1 for the top left node. Every squad publishes contents with the sequence number under its prefix. Then, the company commander, located at the bottom right corner, collects reports from the subunits by simply specifying /company as a topic to subscribe. Two different algorithms are used in this experiment. The baseline subscribes to 16 publishers all the time, while PubSubSum adaptively controls the number of subscriptions by considering the network condition. Two different network speeds are tested, 110 megabits. We consider non-redundant context here. So, yeah, that's the important thing. And in this experiment, content generated by the same platen at the same time is considered redundant. In other words, since the squads in the same platen are geographically close to each other, their reports can be considered as redundant. So non-redundant items are those generated at different time or by different platen. In this case, the difference between pop-up sum and baseline becomes more dramatic. And the research shows that the number of collected non-redundant content item from each platen over time. The research denotes that pop-up sum collected non-redundant reports faster than the baseline in both networks. Notably, in the constrained network, pop-up sum achieved more than 75% information coverage by the end, while the baseline attained lower than 50%. These results express the main strength of pop-up sum, quickly summarizing content by recasting less redundant data objects. In addition to this figure shows the counts of the non-redundant reports from the platens. As before, pop-up sum achieved better information coverage than baseline, especially during the congestion period, which starts from 30 seconds to 150 seconds. The Mininet simulation showed that the implementation worked very well as designed, and in the next experiment, we wanted to verify that it operates on real device. We constructed a simple testbed with 4 Raspberry Pis as publisher and a desktop computer as a subscriber. Raspberry Pis equipped with cameras published the snapshot image every second. 2 of them viewed one side of scene, and the remaining 2 viewed the other side. So it referred from the nodes name in the figure in this figure. The desktop, the subscriber, then collected the published image and displayed them on the screen as they were being updated. Using the testbed, we tested a congestion scenario similar to the previous experiment. Since the testbed supported 100 megabit full duplex for the Raspberry Pi and 1 gigabit full duplex for the desktop, we needed to manually downgrade the speed simulator to simulate the congestion using the software called ETH2. The figure explains that. This figure explains that the subscriber reached the maximum network capacity when the network becomes congested. However, the congested network was still able to get streams from all 4 cameras as shown in this figure. When ETH2 changed the network speed, the number of subscriptions dropped, but it recovered to 4 quickly when the network was reconnected. The number of retrieved images was higher in the constant phase, while the speed was a bit slower during the congestion period. So in conclusion, all this work describes pop-up sum, a content sampling-based pop-up protocol, pop-up pattern on information centering network. It selectively subscribes to the available publisher in the network by considering source redundancy. And pop-up sum diversifies not only content for a particular source, but also the source themselves. It also describes how to handle network congestion by adaptively controlling the number of subscriptions, jointly working with the traditional approach. And in the future, we plan to extend this work to satisfy real-time constraints from applications so that the algorithm optimizes the network resource while meeting the given constraint. And thank you for listening today.